Okay, this is the notes for section 5-6, solving systems using matrices. If you haven't done so already, please stop the video and read the section first, and then go ahead and continue with the video. This is another way that we can use to solve matrices. We've looked at using linear combinations, we've looked at substitution, we've looked at using your CAS, we've looked at tables on your CAS and graphing using your CAS. So this is kind of our final new method of solving systems, and it kind of explains why we've been doing these inverse matrices in section 5.5. So basically, if we have a system of equations in standard form, we can solve that system by putting the system into matrix form and then using inverse matrices to solve it. Okay. So let's take a look at example 1 here. It says write the matrix form of the system 3x plus 4y equals 6 and 2x minus 7y equals 2. In your reading you should have noticed an example problem similar to this, but if you think about it, we can take the coefficients on the left hand side. Once again, this needs to be in standard form in order for us to do this, but if I take the coefficients on the left hand side and write a matrix out of them, and if I multiply that matrix by xy, it should be equal to what we're going to call our constant matrix, which is 6, 2. Okay? So here's what that would look like then. So I have my coefficient matrix, and that's what we'll call that, the coefficient matrix, times xy equals 6, 2. Now, if I do my matrix multiplication on the left hand side, I'll get exactly what I have up here on the left hand side. And obviously 6, 2 can just be written as 6, 2. So if we multiply that out, we will get the exact same system that we started with. Okay, so to solve a system that we have in matrix form, and that's the first thing we need to do is write it in matrix form. What we can do is we can multiply both the left and right hand side of that equation by the inverse of the coefficient matrix. By doing that, if I take the coefficient matrix times its inverse, that stuff on the left hand is going to cancel out, and I'll be left with xy, which is what I'm looking for. So I'm going to start, when I'm doing that problem, by writing that a system in matrix form. Okay, and then the next thing that I'm going to do is I'm going to multiply the left and right hand side by its inverse. Okay, now you'll notice how, remember, multiplication of matrices is not commutative, so we have to do it in the same order. So I'm going to put it on the left hand side here, because over on the right hand side of the equation, in order for us to multiply these two together, it has to be listed first, because then I have a 2 by 2 times a 2 by 1. Okay, so if I do that on the left hand side, the coefficient inverse times the coefficient matrix, just gives me xy. So when I do that, I get xy is equal to whatever we have on the left hand side. Okay, and you can use your graphing calculator to multiply that out. When you do that, you end up with 26, negative 2. Okay, this method also works really well for solving systems with more than 2 equations. So if we have 3 or 4 or 5 equations within the system, that we can use the technology of our calculator to kind of help us with the grunt work that might be involved with solving a larger system. So what we want to do first of all is we want to make sure that that system is in standard form. So all the variables should be in the same order on the left hand side, and then set equal to some constant on the right hand side. Remember, if one or more of the equations is missing a variable, you need to put a 0 in that place. So the first step, and probably the most important step, is getting the system written in matrix form. So that's the first thing that I want to do here, is I want to make sure that my system is written in matrix form. And I've done that here, and you'll notice that on this middle equation there was no y term, so I needed to make sure that there was a 0 in that place where the y was. Okay, so the top equation, the coefficients are 1, -1, and 3. The middle equation, it's 1, 0, and 2, and then finally 2, 2, and 1. Okay, then we would multiply that times x, y, z to get 9, 3, and 10. Okay, so I'm going to call my first matrix A this coefficient matrix, and the second matrix B our constant matrix. Okay, so if I'm going to solve this, if I multiply both sides of this equation by A inverse, I will have what I'm looking for. So that's exactly what I'm going to do. Is I'm going to take, I know that x, y, z will be equal to the inverse of A times B, which is the coefficient matrix inverse times 9, 3, 10. And if I multiply that out on my calculator, I get 35, -22, -16. And as you can see, that's a much easier method, using the technology to help us to solve three equations and 3 unknowns, as opposed to that linear combination method that we did back in section 5.4. Okay, next I'd like to take a look at how we can look at the number of solutions that a linear system will have based on the determinant of the coefficient matrix. And the way it works is this, is that if you have an n by n system of linear equations, the equation has exactly one solution if and only if the determinant of the coefficient matrix is not 0. So as long as we have an inverse to that coefficient matrix, in other words, the determinant is not 0, there would be an inverse. When that happens, we will always have exactly one solution to that system. Okay? Now, if the determinant is 0 in the coefficient matrix, then there is no inverse, and we have one of two situations. We either have no solutions or infinitely many solutions. Okay? And to determine whether or not there's no solutions or infinitely many solutions, what we need to do is we need to just find a solution to one of the equations and test it in the other equations to see if it works. So let's take a look at example 4 then. It says, consider the system 6x minus 9, y equals 12, and 2x minus 3, y equals 4, and show that this system does not have exactly one solution. Well, like we said above, all we have to do is look at the coefficient matrix and find out if the determinant is 0 or not 0. Okay, well, to show that it doesn't have exactly one solution, that means the determinant must be equal to 0, and let's check that out. Okay, so if I look at the determinant of A, I'm going to take 6 times -3, AD, minus BC, so minus 2 times -9, would be equal to -18 plus 18, which is equal to 0. And we know from the system determinant theorem that that means that there is not exactly one solution. So there's either 0 solutions or infinitely many solutions. Okay? So part B then says, determine how many solutions this system has. Well, to do that, what I'm going to do is I'm going to look at a solution for one of the equations and see if it works in the other one. Okay? Well, if I look at the point 2, 0, if I plug 2, 0 into my first equation here, 6 times 2 is 12, minus 0 is 12. So I know 2, 0 works in the first equation. Now I'm just going to check to see if it works in the second one. Okay? Well, 2 times 2 is 4. 4 minus 3 times 0 is 0, so 4 minus 0 is still 4. So it works in both equations. And all you need is one point to work in both equations, and then you know there's infinitely many solutions. So it's all a matter of just checking one point. It either works in both of them or it doesn't work in both of them. It either works in just one or in both.